All right, hello. Today we're going to be moving on to a completely new topic. We've been talking about carbonyl chemistry for quite some time, and what we'll be moving to now is chapter 23 in your textbook, and we're going to get into the functional group called the amines. Now, personally, this is my favorite functional group, if you can have one, in all of chemistry, and a lot of that has to deal with my background in looking at compounds that are interesting both in plant sources as well as neurologically active chemicals. So amines show up in a lot of those two groups, and what we're going to do first is look just at the nomenclature, well, not detailed nomenclature, but just how we construct these amines, right? So they're all based off of the structure of a compound that is technically not an amine. This is the molecule ammonia. All right, so ammonia is something that we've studied for quite some time, including in general chemistry. If we replace one of the hydrogens on ammonia with an alkyl group, an R, then we make an amine. All right, so this is called a primary amine. And the way you look at this is you just say how many alkyl groups are attached to the nitrogen. If it's one, then it's primary. If it's two, then the amine is secondary. And if there are three, then the amine is tertiary. And that's it. All right. Now, there is a few exceptions here. Ammonia is technically not an amine. You either can be a primary, secondary, or tertiary amine, and that's it. However, a tertiary amine can react with an alkyl group to form an ammonium-like ion, and this is called a quaternary ammonium salt. All right, so this is technically not an amine either. So what makes up the amine is the nitrogen atom with the lone pair and at least one alkyl group. So this guy's an amine, this guy's an amine, and this guy's an amine. So really that's just kind of, semantics, if you will. But the R group could also be aromatic. All right, so if we were to look at this compound, this is the molecule aniline, which we saw back in our benzene derivatives chapter. All right, so aniline is what we call an aromatic amine. It's simply just an amine that is in or attached to an aromatic system. All right, so pyridine also is an aromatic amine. And we saw this guy back in our aromatic discussion. All right, so here we have a nitrogen heterocycle, which means we have a nitrogen atom in a ring system, and this ring system happens to be aromatic, and pyridine is an aromatic amine as well. All right, so the difference between pyridine and aniline, obviously, is that the nitrogen is exocyclic in aniline and heterocyclic in pyridine. All right, so that's kind of the basis of the nomenclature I want to cover. All right, so when you go into the nomenclature of amines, it's quite complicated. All right, and we haven't been really hitting nomenclature as in I'm going to put it on an exam or a quiz. So I'll be saying names of amines, and I'll try to explain why they have that naming. So some very simple, straightforward ones, all right, are the primary amines. And simply what we do there, if we want to use the common naming system, is let's take a look at this amine. So that is an amine with a methyl group, so we simply just call this methylamine. And that's its common name, and that's what almost everybody would call it. It does have a systematic name, which I'll write below here in red. It would be called methanamine. So just need to be familiar with those two pronunciations, methylamine and methanamine. I rarely hear people call that methanamine. We typically use the common naming system. So when we move to secondary amines, what we're going to have here is something like this guy. Oops, we need a nitrogen. So if the two groups are the same, then we just simply call this diethylamine. Nope, sorry, it's methyl. All one word there. All right. So we have two methyl groups that they're the same. So if they're different, right, we choose the one that goes first alphabetically. So this would be N-ethyl. All right, so we have to put the N there because we have to indicate that the ethyl group is on the nitrogen, and then we'd say methylamine. All right, so the ethyl goes first due to alphabetics. All right, and tertiary amines would be the same, where you would have your groups listed in alphabetical order, and the N's indicate that your groups are attached to the nitrogen. All right, so we're not going to get too deep into the weeds here with nomenclature of amines, but I do want to show you some really cool ones that really fascinate me when I talk about the amines themselves. All right, so one place you certainly will see the amines a lot are in these compounds called alkaloids. So alkaloids are amines sourced from plants. And the reason they got this name is because if you were to put these so-called alkaloids into aqueous solution, all right, the pH would be slightly alkaline or above 7. So they called them alkaloids, and that name's kind of stuck. All right, so these are amines that are sourced from plants. All right, so there's a lot of cool ones out there. One that we certainly see quite a bit is the molecule nicotine. So that's a methyl group there. So it contains two amino groups, all right, one there, all right, and then one here. So this is nicotine, if I could spell it right. Right, so that is a naturally occurring alkaloid, and there's several other ones that are quite neat. Things like morphine, quinine, atropine. There's lots of them out there. Cocaine, for example, is another one that is naturally occurring. All right, and quite familiar to us. All right, so other ones that are out there, histamine. All right. Histamine is not technically a alkaloid. I don't think it comes from plants. It is expressed in our nervous system and other places in the body. And it's most famous for being active in allergic responses. So when we have an allergen in our body will react by releasing histamine, which is a vasodilator. It'll open up our, what do you want to call it? Sorry, I'm not good at biology. The veins, so we can get blood through them much easier. But it also causes all kind of different problems like watery eyes, runny nose, and believe it or not, the secretion of acid in your stomach. So there could be some bad things that happen when too much histamine is released. So there are these molecules called antihistamines, and these are quite familiar, especially this time of year, where we look at things like Allegra, Zyrtec, and these are what we call trade names, but they are organic molecules that are designed to stop the release of histamine. So other ones are also stomach acid reducers. They'll also work as an antihistamine to reduce the amount of stomach acid that's being released. Another cool amine out there is one that is based off of the following structure called a 2-phenethylamine. So here we call this 2-phenethylamine because we have the amine at carbon 1, and at carbon 2 we have the phenyl group. All right, so there's a lot of neurochemistry or neurotransmitters, if you will, that are based off of this structure. All right, so some that we look at are things like adrenaline, All right, so when I draw the nitrogen like this, I'm not showing the lone pairs, although I could, which I just did. All right, but I'm also showing the hydrogen just kind of sitting on top of the nitrogen. I'm not showing the NH bond, but unlike carbon, I do have to show any hydrogens that are bonded to it. All right, so it's just like the OH over there to the left. I just draw the H, not showing the actual literal single bond between them. But this is the molecule adrenaline, also called epinephrine. And as you can see, it's based off that 2-phenethylamine structure. All right, some other ones out there are, of course, methamphetamine or things like mescaline. All right, so there's a lot of really interesting neurotransmitters that are based off of this 2-phenethylamine. And finally, the one I want to look at that I find quite fascinating are off of the indole system. So indole oops, it has an H there. All right, is an aromatic amine. All right, it's got a 5-membered ring fused to a 6-membered ring. All right, so this is what we call a privileged structure in medicinal chemistry. So it's used in a lot of drugs, and it's a very widely expressed natural occurring nitrogen heterocycle. All right, so the molecule serotonin is a neurotransmitter, and it is based off of the indole ring. There's the OH group here. So this is serotonin, right? And of course, a neurotransmitter. And there's a lot of interesting drugs, natural products that are based off of this, I guess you could call scaffold, that are interesting in or what you call neurochemistry. All right. And of course, we could keep going on. Things like the opioids that are getting a lot of national attention right now are also amine-based compounds. So in the interest of time, we're going to kind of move on. You can kind of tell these are fascinating, at least to me, a fascinating functional group. All right, so obviously they're important in a lot of neurochemistry or in plant science. So it's going to be useful to know how to prepare them. So the preparation of amines is what we're going to be looking at next. Some of this may be a review, all right, but we're going to kind of look at 3 ways in which to do this. First, we're just going to look at nucleophilic substitution. Using nitrogen nucleophile. Next, we're going to look at reduction of nitrogen-containing functional groups. And finally, probably my favorite reaction in this list is something called reductive amination. And the reason it's my favorite is because in graduate school, one of my projects hinged on making amine through this reaction, and it took months to get the reaction to work. And so during that time, I couldn't stand this reaction, but at the end, finally getting it to work, it's got a special place in my heart. So anyway, we've been talking about nucleophilic substitution first. All right, so one way you may think about this is, all right, I can just simply take ammonia and react it with iodomethane. All right, so this is an RX, if you will. How about I don't write it backwards? It might be a little more straightforward if I do it this way. All right, so what we've got here is our RX. And as you'd imagine, we have a nitrogen that is nucleophilic. All right, it has that lone pair. And I'm going to cheat and put a little bond in here and break it. All right, so you can imagine that here we get this ammonium salt, like so. All right. And what can happen in a subsequent step is a second molecule of ammonia can come and remove a hydrogen, and that would give us a primary amine. And an ammonium salt. All right, so looks straightforward. The problem is that here we start with ammonia, and now we get methylamine. Turns out methylamine, since it has this electron donating methyl group in it, it is more nucleophilic than ammonia. So what happens is methylamine will react with iodomethane to produce dimethylamine. Well, dimethylamine is more reactive than methylamine, so it reacts again and again and again until it cannot react anymore. All right. So what we wind up with is a reaction that we cannot control this way. So it'll work if you want to go all the way. So this is something that we've called in the past exhaustive alkylation. All right. So what happens here is we're going to need an excess of the iodomethane, and we're going to do an exhaustive alkylation to give our quaternary ammonium salt. All right, so the reaction does not stop very cleanly where you want, and it's very, very, very difficult, if not impossible, to isolate just a primary amine from this reaction process. So this isn't a good way to make an amine technically. It's a wonderful way to make an ammonium salt, but technically we're after making an amine. So pretty clever synthesis was developed called the Gabriel synthesis. And this will use something called a phthalimide. All right, so let's draw that. So if we were to take this compound and treat this with something called potassium hydroxide, which we've certainly seen before, it's a strong base, we can remove that acidic hydrogen there on the phthalimide. So when we remove it, we get a nitrogen nucleophile right here. So this thing is called potassium phthalimide, all right? And it's spelled quite strangely, so PHDH. Okay, potassium phthalimide, all right? So that is going to wind up being our nucleophilic source of nitrogen here. So why the weird molecule? All right, it's that we need the electron withdrawing carbonyl groups, all right, to pull the electrons away from nitrogen to make this hydrogen here delta positive. All right, so that's what the strange setup's for. And this starting material is quite easy to make from ammonia and phthalic acid. All right, so from a historical standpoint, it's quite easy to prepare. So what we can do with potassium phthalimide is we can use it as our nucleophile. Technically, it has 2 lone pairs here. All right, and I can go back and use methyl iodide as my electrophile, my RX, if you will, and just do a simple attack here. And now I will alkylate that nitrogen and produce potassium iodide in the process. All right, so now I have the precursor, and what I can do here is one of several things to kind of blow this thing up to get back my amine. All right, it can be done with either hydrazine, base, or even acid. We just need to get this thing to release, and one way that is done is with strong base. All right, in the presence of water, and this is a hydrolysis. And this is going to give me my amine. All right, so where's that coming from? I've got this NCH3 here, all right, and then my hydrolysis. Okay, so water is going to supply these 2 hydrogens onto what was incorporated into that phthalimide. All right, and my byproduct is going to be, in this case, since we're working in base, the conjugate base of phthalic acid, which is called phthalate. All right, so that's my byproduct. Not so important that we know what the byproduct is, more important that we know what our amine is. So to summarize, this synthesis, what I can look at here is looking at taking potassium phthalimide and in a 2-step process, you take RX. Let me change the color. Change it to red. And then here I need hydroxide and H2O. Now again, if this were acid, all right, or even something called hydrazine, which is N2H4, it will also cause this hydrolysis. But nonetheless, what we're going to be looking for is this guy right here. And what's nice and clean about it is it makes a primary amine very cleanly. All right. So this is a very effective way in which to make a primary amine. All right. Okay. So the next class of reactions that we're going to look at are the reductions of nitrogen-containing functional groups. Okay, so we've seen some of these before. All right, so if I look at, let's take just nitrobenzene, I can reduce the nitro group down to an amino group. Right, we've seen this before, and ways we can do that. So what I'm going to do is put H in brackets. So whenever you see H in brackets, that means reduction, right? It doesn't mean concentration of hydrogen like it did back in general chemistry, right? It is reduction. And the opposite is if I put an O in brackets, that means oxidation. So what I'm going to say here is methods that we can use to do our reduction. We've seen before iron, hydrochloric acid, tin and hydrochloric acid. And we even saw catalytic hydrogenation, where we used palladium on carbon in the presence of hydrogen gas, and sodium borohydride can sometimes be effective as well. All right, so any of those 4 will be an adequate way to reduce a nitro group to an amino group. All right, so good, we got an amine there. Some different reductions that we have seen are of the carboxylic acid derivatives. All right, both amide and nitrile can be reduced with lithium aluminum hydride, followed by an acid quench. So this will give primary amine. And we can reduce an amide as well. And what's cool about reducing amides is they can be primary, secondary, or tertiary depending on what the nature of these two groups are here. All right. So if they're hydrogen, then you have a primary amine. If one of them is alkyl, then you have a secondary. And if both of them are alkyl, you have a tertiary. All right. And another one, I don't believe it's discussed in your textbook, but we can also reduce something called an azide. Let me get this Lewis structure correct here. Okay, that is one acceptable Lewis structure. And this is called the azide. And it's most often just abbreviated as N3 for, as you can see, simple reasons. You don't have to worry about which Lewis structure you have. All right. But that's the azide, and that can be reduced with lithium aluminum hydride and following by a quench to give a primary amine as well. All right. So what's different between doing it with the azide and the nitrile? All right. So look here at the nitrile. We have RC and then N. So RCN. And then in the azide, we have RN. So we get RN right there. Okay. So we get the primary amine, but we don't have that carbon spacer, right, between the R groups. So that may be of some synthetic interest, all right, in the future. Okay, last one I want to talk about is reductive amination, and I'll actually go ahead and just stop this video here, and we'll get into reductive amination in the next video. So see you then.